so let's get kind of back to where we left off on Monday, which was talking about the binomial distribution. Oh, for those of us in class, hold on. Talking about the binomial distribution. So we had this function that we kind of talked through. Kind of the main new thing was this factorial, right? So I think we kind of ended, we went through this coin example. We said, once we identify the three pieces of information, which was n, the number of trials, x, the number of successes we're looking for the probability of, and p, which was the probability of success in any one of those trials. Right? Once we plug those in, it's really just a little bit of making sure we can get this entered into our calculator correctly. Okay. So I think, I can't remember if we worked through this, so I'll just pick up here. Let's say we have this example where we've got 5 students. Or 5 adults, okay? So you can kind of think about asking each adult is the experiment, so I'm running this experiment 5 times, right? I know that the probability any one adult has a 4-year college degree is 30%, or a probability of 0.3, okay? And I want to find what's the probability that exactly 3 of those 5 have a college degree, okay? So what I'm looking for is the probability that x, this random variable, right, which is the number of people who have a degree out of the, where is it, 5, is so the probability that x is equal to 3. Okay? So I've got those 3 pieces of information, right? The number of trials, the probability, or number of successes I'm looking for the probability of, which was 3, and then the probability that if I asked any one of those people, the probability they had a degree would be 0.3. So really it's just a matter of getting those values plugged in this equation and making sure we can work through this correctly. Now we talked about these factorials. 5 factorial was like 5 times 4 times 3 times 2 times 1. And sometimes, even if we haven't found that factorial button on our calculator yet, which, like I said, whatever calculator you're going to use, make sure you can find that, especially coming up closer to the exam. But if we write this out, a lot of the times things cancel, and this quite often simplifies. So I think I ended the last class with showing, even if we had like 100 factorial, but if it was over 99 factorial, so our n was 100, our x was 99, a lot of this would simplify if we kind of write out the first few numbers in that factorial. Now we can kind of see that things are going to cancel quite a ways down. So, our calculators are often limited, depending on the calculator and how high up we can actually use that factorial button. So a lot of times writing this out will help us. So I think that's kind of where we left off, kind of this idea of how we identify these three pieces of information and then plug them into our binomial function. So here we get the probability that x is equal to 3 is 0.13. So the next question is going to be everything's exactly the same, but I want to know what's the probability that 4 of these people have a degree. Right? So I'm going to jump the gun a little bit, and we're going to allude to, or I'm going to allude to something we'll talk about a little more detail later. But let's think about. Make the number a little bit easier to think about, and then we'll come back to this example. So let's say our number of trials, the number of people we ask here, instead of 5, let's say it was 10. Okay? If the probability that any one person has a degree is 0.3, on average, if we just asked 10 random people, how many people would have a college degree out of those 10? It's 30%, we've got 10 people. On average, 3 people, right? That's like the typical response we would expect. Okay? So that would essentially be our mean, right? It's the kind of typical, the average response you would see. Now, on any 10 random people, maybe sometimes we ask and 5 of them have degrees, or sometimes maybe it's weird and 10 of them have degrees. But if only 30% of the population has a degree, it'd be very unlikely that 10 out of 10 have the degree, right? All 10 have a degree. So what we can start to think about is, whenever we want to use this idea, and I'll jump ahead and come back. Oops. That really what we did there in our heads, and the reason why I chose 10 is because it's an easier number to think about. But to find the mean response, or the average response for a binomial distribution, you just take the number of trials, 10, and multiply it by the probability of success, 0.3. 10 times 0.3 was 3. If I flip a coin 100 times, and it's a regular coin, on average, what would be like the most common number of coin flips that come up heads out of those 100? 50, right? What did I do there? 100 was my number of trials. 0.5 would have been my probability of success on any one trial. 10 times or 100 times 0.5 is 50. Right? So I think this is fairly intuitive. Like we could probably maybe arrive to this point without needing this formula, but this is the formula that will give us the mean, okay? So if we think about that example where instead of 5 people, I'm asking maybe 10, we said on average we would see 3. So the probability of 3 should be relatively high. It's the middle of the outcomes that we could see, or it's the average response we would expect to see out of those 10 people. And then I said, well, what if, what's the probability? Okay, let's say 7 out of 10. Well, it's not near as likely, right? What about 10 out of 10? Well, that's even less likely. That's kind of intuitive, but really what happens is once we look at the mean, if we move to outcomes further away from that mean, they become less and less likely. So let's switch over here. Oh, stop share. There we go. So what I'm really thinking about, I'll use this one, is, and we'll go back, right, and think about our specific example, okay? So instead of 10 people, we only had 5 people, right? So the number of possible outcomes we could see were 0, 1, 2, 3, 4, or all 5 people have a degree. Right? If the average out of 10 people is 3, the average out of 5 people would be half that, or if we think about that equation for the mean, 5 times 0.3, we get 1.5, okay? So we know that, it was easier when I was thinking about the example where we had 10 people because the average was 3, so the most likely outcome we would see is 3. If I end up with a mean that's not an integer, well, I know that this is a discrete random variable, right? I have to see an integer value. So if I get that the mean is 1.5, what it's really saying is the most common outcomes would be 1 and 2, okay? So when you kind of think about it, if we were, and remember what's on the, if I want to think about what's on the y-axis here, and I'll move my arm out of the way in just a second, right? Our y-axis is really representing the probability that we see these different outcomes. So with a mean of 1.5, 1 and 2 are the most likely outcomes to occur. As I move further away from that mean, right, I was saying like probably 7 out of 10 and then 10 out of 10 people. Same kind of thing here, even though we only have 5 people. As we move away from that mean, the probability of seeing these higher outcomes starts to decrease. Or if I move in the other direction, the probability of seeing these values lower than the mean start to decrease. Right? So once I identify that mean, as I move to outcomes further and further from that mean, those probabilities start to decrease. Okay? So what we had just found was the probability that we see the outcome of 3, right, x is equal to 3, was about 0.13. So what do we know has to be true about the probability x is equal to 4? Well, the probability that equals 4, it's further from that mean of 1.5, so it should be lower. Right? So we'll go back, we should be looking for a probability lower than 0.13. Okay? Any questions on that? Let me make sure I can see, there we go. Okay. And let me show this here. So if anyone's still kind of working, you'll be able to see this. Hold on, I'll make this a little bit bigger as we work through this stuff. So if you're still kind of copying this down, it'll be here in the lower corner. Okay, so if we're looking for the probability that 4 of them have a degree, we said it has to be less than the probability that 3 of them have a degree. Well, we just found the probability that 3 have a degree is 0.13, so we know the probability has to be less than that. The only answer here that makes any sense is A. Right? So sometimes if we had done some, previous work, right? I don't know why this classroom does this. I was using this in another one. It automatically switches over. So if we know the probability 3 is 0.13, the probability 4 has to be lower. The only answer here that makes sense is that 0.028. Now I could go ahead and plug everything into the equation again, right? My probability of success is still 0.3. I'm still asking 5 people, so my number of trials is 5. It's just now x would be 4. Right? So I've got those 3 pieces of information I need. Go ahead, plug them into that binomial equation, and I'll find sure enough it is that 0.028. Right? But knowing this idea that, yeah, as I move away from that average response, the outcomes that are further and further from that response are going to be less and less likely. Right? That's how the binomial distribution works. Think about flipping a coin. And what's the probability if I flip a coin 100 times that 70 of them come up heads? It seems kind of unlikely. Well, what's the probability 90 of them? Really unlikely. What about 100 out of it, right? As I'm moving away from that middle value, that mean of 50 out of 100, those probabilities we would expect to decline. Okay? Any questions on that before we keep moving here? Yeah, so since you just asked that, so one thing I posted after class Monday, which I said I was going to, I'll minimize this now, was there's an exam one practice material. So one thing that I've kind of already created for you, I'll look at the PDF because I think it shows up better on the web browser, if I recall. Right, I kind of give you any equation that you could need, right? Now, what I would suggest doing is prior to the exam, going through this and making sure you can identify exactly what these, what these equations represent. And I even group them, like here's kind of our weighted mean and our weighted variance. Here's our probability laws. Here's our binomial equations. We'll talk about some more of these today, but yeah, this will be kind of, that's already out there. So yeah, you'll have that. Yep. So, oops. Any other questions before we kind of keep moving here? We good? So what's the probability? I'll leave this since I already have it drawn. What's the probability instead of exactly one number? We introduced the idea last class of cumulative, right? Cumulative mass functions. Well, what's the probability at least 3 out of 5 have a degree? Okay. So we want the probability that 3 out of the 5 have a degree. So the easiest way to think about this is if I'm looking for, just write down what I'm looking for. So at least 3 would mean that x could be greater than or equal to 3. Right? So what I'm going to do is write down all the outcomes that meet this criteria and just add the probabilities up, because I can't see exactly 3 people and exactly 4 people out of the 5 have a degree, right? It's either one of the two. So it goes back to last class, I talked about this idea. If we don't have, these are mutually exclusive events, right? When we look at these discrete outcomes, and so there is no intersections. So it's simply whenever I'm looking for the probability of an event here, we could call this event A, right? It's really just going to be all the outcomes in that event, the probabilities of those outcomes added up, right? And since I only have 5 people, it would kind of stop at 5, right? Now, this is kind of a, it's not the easiest thing in the sense that every time, and sorry, this is a 5 if you can't see it. Every time we're looking for the probability of exactly one number of outcomes, we have to use that binomial equation. So I'd have to use it 1, 2, 3 times here to find the 3 different probabilities. Now, lucky for us, the way I set this up, right, I already found this was 0.13, this was 0.028. So at this point, all we have to do is find the probability that x is equal to 5. Okay? And I think I also ended on this last class, but I'll kind of give you a reminder. Let's say we were trying to find that probability x is equal to 5. Right? So we start plugging that into our equation. So n factorial over x factorial. Well, if we're looking for the probability x is equal to 5, notice n and x are the same thing. So it's 5 factorial here, n minus x factorial, right? Times the probability of success to the x power, times 1 minus the probability of success to the n minus x. So anytime we're looking for the probability that all of the outcomes are the success, right? Or are, whatever we define that as here, does this person have a college degree? 5 minus 5 is 0. I'm going to do the easy math first. 1 minus 0.3, that's 0.7 to the 0, 0.3 to the 5th. Notice here, 5 factorial divided by 5 factorial, that'll cancel. And one thing we said last class is this becomes 0 factorial, and 0 factorial is simply equal to 1. So with that in mind, right, this whole fraction is just 1, right? Everything cancels, and then we have 1 over 1. 1 divided by 1 is 1. Multiplying anything by 1, we can essentially ignore that. Right? It doesn't change anything for us. Also, I think I alluded to this, and if I didn't, we'll hit it now, but anything to the 0 power should be what? 10 to the 0 power and 100 to the 0 power is just 1. Okay? You can kind of verify that in your calculator. I had a section yesterday that someone, I don't think they believed me. I saw them, they were typing it in and looked surprised. So it is 1, right? Anything to the 0 power is 1. So 1 times 0.3 to the 5th times 1. So you can essentially ignore the 1s, and when we want all the outcomes to be successes, it's just the probability of success in any one trial to the power of however many trials we have. So if we enter this into our calculator, if the probability that x was equal to 4 was 0.028, the probability it's equal to 5 is going to be even smaller, right? I mean, when we went from 3 successes to 4 successes, we went from 0.13 to 0.028. So you can imagine once we go to 5 successes, this is going to be like, I don't know, I can't remember what it is, but it's a really small number, right? There's a lot of zeros after that decimal point. So we plug that into our calculator here. There we go. Switched over right that time. All right, I'll kind of leave this up here as if you were kind of still jotting some of this down. So all we're looking for there is a probability x is equal to 3 plus 4 plus 5. Now, I'll come back to this in a second. We'll hold off on this line, but I'll allude to how maybe this would help us in other situations. So we find that it's 0.002. Yeah, it's pretty small. So all we have to do is then add these 3 up, and now we've got the probability x is greater than or equal to 3. So all we did there was what outcomes meet that criteria of x being greater than or equal to 3, add them all up, and then we'll get our answer. Okay. Any questions on that before we keep moving? Okay. What did I have next? I had the mean. I think I want to go through one more thing here with this example. So I found the probability x is greater than or equal to 3. Okay. There's another way I could have done it. It doesn't save me a lot of time in this example, but in other examples it would have. So I'll kind of walk through that. So let's start out, get rid of these papers. What we were looking for was the probability x is greater than or equal to 3. Let's call that event A. Using the complement rule, I know that I can always find the probability of an event using 1 minus the probability of its complement. So what would the complement of x greater than or equal to 3 be here? Complement is just everything that's not an A. So here it would be x is, well, remember, our event A is not that it's equal to 3, it's that it's greater than or equal to 3. So A complement would actually be that x is just, you said the outcomes, but less than 3, right? Anything that wouldn't be in event A, which would be 0, 1, and 2. But I think the better way to get kind of used to writing this is, right, it's just anything, even if this was a continuous variable, then the complement, it would just be less than 3. Now, once we think about what outcomes are less than 3, well, that's just the probability. What's the very first outcome that's less than 3 if it's discrete? X could be 2. What also is in this, meets this criteria? Well, then the next outcome we could see would be 1. And then the final outcome that we don't want to forget about, but it is a little bit easier to forget about, is that's equal to 0. Right? I'm going to run out of space here a little bit. I'm used to writing on a whiteboard and not having that problem. So now we would still have to use that binomial equation 3 times. So in this instance, using this complement rule didn't really save us a lot of time. We could have done it this way, though. If we were starting from scratch and didn't have any of the previous work done, this would have taken us just as long as finding it the other way, because we'd have to use that binomial equation 3 times. But what if I had an example where, I don't know, I had a lot more trials, and, well, I'll give you an example. Let's say I use the coin flip example. So I flip a coin 100 times. What's the probability that I see at least, or sorry, I see 99 or fewer of those 100 coin flips come up heads, right? So what's the probability that the number of successes I see in those 100 coin flips is 99 heads or any outcome less than that? Well, first of all, this probability should be pretty close to what? If I flip a coin 100 times and say, what's the probability that I see 99 or fewer of them. Well, no, so think about it this way. What are all the possible outcomes I could see? I could see 1 of the 100 come up, or 0 out of 100 come up heads, 1 out of 100 come up heads, 2 out of 100, all the way up to 100 out of 100. If I want to know what's the probability that 99 of them, or any number below that is the number of heads I see, that's almost every outcome, right? I mean, the only outcome that this doesn't, have in it is the probability that all 100 come up heads. So this probability, this cumulative probability, should be pretty close to what? If I start writing this out, I mean, if we think about this, what's the probability 0 out of the 100 are heads, plus what's the probability 1 out of the 100 are heads, plus all the way up to what's the probability 99 out of the 100 coin flips are heads. I've almost added up the probability of every single possible outcome except for 1. So if I add up the probability of every single outcome we said last class, those should always add up to 1. So this is going to be really, really close to 1, right? Because the only probability it leaves out is the probability x is equal to 100, which, what's the probability that if you flip a coin 100 times, all 100 come up heads? Pretty low, right? We can figure out how low it is, but it's pretty low. Okay? So we know this is going to be close to 1, but exactly how close and what's the exact value? Well, I don't want to have to use the binomial equation. What here would be 9 or 100 different times? That's insane. I would never ask you to do that. But if we think about what we're looking for is the probability of A, we know that we could rewrite that as 1 minus the probability of A complement, which here, if our event A is at x is less than or equal to 99, A complement would be that it's greater than 99. What are the only outcomes out of 100 coin flips that we could see that meet this criteria? Well, the only outcome greater than 99 that we could see, since we only flipped the coin 100 times, is the probability that x is equal to 100, right? Now I only have to use that binomial equation 1 time. I can easily do this as opposed to using it 100 times if I didn't use that complement rule. Okay? So that complement rule becomes pretty important to us. And kind of the idea here of a cumulative mass function, it's the probability x is equal to 99 plus the probability of every outcome below it. Okay. Any questions on this? Okay with this? Yeah. All right. So let's go back. There we go. So we already kind of talked about this mean, right? How we find that. That was pretty intuitive. To find the variance, unfortunately, is not very intuitive. And I'll switch this so people don't. There we go. So we could look up the mathematical proof, but because of that equation, that probability mass function, that's our equation for the binomial, no matter what n is or what p is or what x is, the variance of these binomial distributions, we can always calculate using this formula. Right? So the variance depends on the number of trials we run, right? If I only flip a coin 5 times, the variation in the outcomes that I could see is much smaller than if I flip a coin 100 times, right? But if I flip it 5 times, I can only see 0 through 5 as outcomes, not a lot of variation in the outcomes I can see. If I flip it 100 times, technically I can see anything from 0 to 100. So there's a lot more variation. So that's kind of captured here because we're plugging in the number of trials. And really, like I said, there's no really intuitive explanation with this formula as to why it is what it is. It's just, if we walk through the mathematical proof, it'll always be this. So kind of notice here, we're taking the mean and we're just multiplying by 1 minus that probability of success. But if I ask you a question like on the exam, hopefully these are easy. I mean, once we know these are our equations, it's pretty easy to plug those values in here. Okay? Now, one thing I'm going to try to really hammer home, I've been trying to up to this point anyways, but if I want to go from the variance to the standard deviation, what's the only other thing I need to do? Take the square root, right? So if we're going, but it helps if I show you the notation, right? Sigma squared is the variance. Sigma is my standard deviation. So if I'm going from the variance to the standard deviation, all I do is one more step, take the square root, okay? All right. So if we're okay with that, right, we've got our variance equation. If I had an example, I'll skip ahead and do this example, right? So let's go back to the college example. I've got 5 random adults, 30% of them have a college degree. What's the mean and the variance? Well, we kind of already talked about the mean in this example. If we take the number, right, we go back, the number of trials, we had 5 people we were asking. The probability of success was 0.3. 0.3 times 5 was 1.5. So we know the mean is 1.5. Now the variance, it's just a matter of, we have 5 people, 0.3 is our probability of success, just plug those in and compute it, right? So if we plug those values in, right, 0.3 and then 1 minus 0.3 was 0.7, we'll get that the variance there was 1.05, okay? So like I said, these ones should be pretty easy, right? Once we have those equations, it's pretty easy to find the mean and the variance. And the mean's very intuitive, right? So if I go back and think about using this idea of the mean, right, I want to hammer home this idea as well. Let's look at this very first graph up here. So I've got n is 5 and the probability of success is 0.1, okay? So my mean there would be what? 5 times 0.1 or 0.5, okay? So I know on average, the outcome I will see is 0.5. Well, it's a discrete variable. I can't actually see the value of 0.5, but if the mean is 0.5, what that's telling me is the most likely outcomes are 0 and 1, right? So here, the two most likely outcomes are 0 and 1. And just because I'm saying they're the most likely, they don't have to be equally as likely. Notice here, 0 is a little bit more likely than seeing 1. But of all the outcomes, 0 and 1 are the 2 most likely, right? They have the 2 highest probabilities. And then as I move away from that mean of 0.5, notice the probability of seeing higher numbers of successes or kind of those higher outcome values, much, much lower, right? It decreases pretty quickly. If I look at the flip side, what if n was 5 and the probability is 0.9? Well, there my mean is 4.5. So 4 and 5 should be the most likely outcomes. Sure enough, if I compute all these probabilities, 4 and 5 are the 2 most likely outcomes. And as I move away from that mean of 4.5, the probability of seeing lower number of successes here decreases. Okay? Are you okay with that to that point? Any questions? Okay. Here we have kind of a weird scenario, right? What if n was 5 and the probability of success is 0.5? So with a probability of success of 0.5, what we're really saying is the probability of the success is the same as the probability of the failure, right? It's the idea of like the probability I see a heads is the exact same as seeing the probability I come up tails, right? So when that's the scenario, so we have a mean of 5 times 0.5 is 2.5. So 2 and 3 are the most likely outcomes. And then as we move away from that mean in either direction, notice the probabilities of these outcomes, or these numbers of successes, start to decline. Okay? But at 0.5, this distribution is symmetric. Notice now those 2 most likely outcomes are exactly, you have the same likelihood of occurring, right? And being the same distance on either side from that mean, these outcomes have the same likelihood of occurring. So we have what we call a symmetric distribution. If we split this distribution at the mean, the left and the right side look identical, or would fold on top of each other. Notice, even if I go to a higher number of trials, right? So instead of n is 5, what if n was 50 and the probability of success is 0.5? Well, now the mean, 50 times 0.5 would be 25. So 25 is the most likely outcome. And then as I move to a lower number of successes or a higher number of successes than 25, the probabilities of seeing those higher successes or those lower successes start to decline, right? Getting further from that mean, my probabilities get smaller. The only difference is, right, it's still a symmetric distribution, but now with a higher number of trials, it's just more segmented, right? It looks a little bit more continuous, but still symmetric. And then I have one over here where n is 20 and the probability of success is 0.2. You know, here what the average would be 4. So 4, sure enough, is the most likely outcome. And then as I move away from that mean of 4, the probability of seeing those numbers of successes further from 4 start to decline. Okay? But what's interesting here is if I have a very low probability, notice I have long right tails, 0.2 and 0.1, I have long right tails, so I have right skew distribution. The binomial distribution, when I have a high probability, 0.9, I then get a left skewed distribution. And then when the probability is exactly 0.5, I end up with no skew, right? I have this nice normal distribution. Okay? So the binomial has different shapes depending on the probability of success. Okay? All right. Any questions on anything before we kind of keep moving forward? Where are we at in time? Okay. So we'll see. I might come back here. I want to do a little bit. We'll skip ahead. I don't really love this. Sometimes it confuses people, but I might end up working through it today. We'll do this real quick, and then we'll go and do a little bit of work in Excel. Okay? So which of the following is not an appropriate situation to use the binomial distribution? So remember, the binomial distribution, we need a success and a failure. Only 2 outcomes. The probability that we see that success is the same on any one trial, and then we run this number of trials, however many times we want to run it. So calculating the expected number of coin flips that come up heads in 123 flips. So I'm flipping a coin 123 times. Could I come up with the mean, right, using the binomial distribution? Well, let's think about it, right? If I flip a coin, the probability it comes up heads is 0.5, so any one coin flip, the probability is the same. Each coin flip is independent from each other. I've got 123 coin flips, and I just want to find kind of what that mean is. Well, n is 123, probability of success is 0.5. This is a perfect scenario to use that binomial distribution. Okay? What about calculating the probability that at least 5 out of 20 patients will get sick or nauseous from an antibiotic? Well, if I know the probability, right, that if a person at random takes this, antibiotic, the probability they get sick, let's say that, I have a number for that, I don't know, 0.2, right? Well, if I'm looking for the number of people getting sick to be 5 or fewer, that's what I've defined as my success, weirdly enough. That's what I'm looking for. And the number of trials to be 20, well, I've got all the components where I could plug those in and find that probability using the binomial distribution. Okay? Calculating the probability, so those 2 are okay. Calculating the probability that an air traffic controller at the Muncie airport makes 3 errors per week. Right? Well, I guess on every landing I could make an error or I don't. So maybe I've got a success and a failure there. But what would my number of trials be here? I don't know, right? I mean, theoretically, the number of planes landing every week is going to change. And I actually don't know how high it could get. I have no idea what the capacity of the Muncie airport is, right? So this is going to be a scenario that is actually going to lead us into the next type of discrete random variable we're going to talk about, which is the Poisson, right? When we kind of have a period of time that we're looking for the number of successes over that period of time, as opposed to a number of successes out of a finite number of trials. So this is going to be a scenario where we can't apply the binomial because we don't have a kind of finite number of trials. We're looking at a time period. And then last, if we know the probability, if we want to find the probability that, exactly 3 out of 5 customers make a purchase once they enter a store. Well, if we know on average the probability that once someone comes in the store, 20% of the time they buy something, so the probability is 0.2. We have number of trials, number of customers is 5. We want to find the probability of 3 successes or 3 of them purchase something. This is a perfect scenario where we can apply the binomial. Oops, looks like my box went a little bit too wide there. So the only one that didn't apply was C. There you go. Okay. So like I said, C, we'll start to see, probably not today, but next class, maybe I'll introduce it today, that we can use a different type of distribution, which is the Poisson for this example. Okay. All right. Any questions here about the binomial? Anything that could change or do differently? Because otherwise, we'll kind of go into Excel for a little bit here. Good? All right. So I kind of have the general form of the equation here, but I'll walk us through this in Excel. I'm going to use this idea of, I was looking this up the other day. So the most recent I could find was 2018. 6.7% of the US population was actually considered millionaires. So, you know, this is like assets and everything. By the time you get to like 70, like this is a very real possibility. So 6.7% of the population is considered millionaires, right? At any one point in time. So I thought it might be interesting. Whoops. I didn't want to hit exit on the, there, I wanted to exit on PowerPoint. So blow this up. Make sure you guys can see it. So what we can do, right, is it's kind of a pain maybe to put those factorials and plug all those values in my calculator and using that binomial distribution equation. So Excel will basically do that for me and spit back out of me the probability. So actually to make it, let's say I want the probability that exactly 5 people out of 100 are millionaires. If I select 100 people at random. Okay? So I know the probability that any one person is a millionaire was that 6.7% or a probability of 0.067. I'm looking at 100 random people, so that's my number of trials, and the number of successes I'm interested in, what's the probability that exactly 5 of those 100 are considered millionaires? Okay. So the first thing we tell this binom.dist function is, well, the number of successes I'm interested in is 5, comma, the next thing I tell it is my number of trials, 100, comma, the probability of success of any one trial was that 0.067, comma, and then the last thing we tell it is, do I want to make this cumulative? Well, here I want the probability that exactly 5 have a degree, so no, I don't want it to be cumulative. So it usually says to put in true, false here. The way I always do this, because it's easier, I mean, for me, is 1 is true, 0 is false. So 0 here would mean don't make it cumulative, right? I just want the probability x is equal to 5. So if I hit enter here, what Excel is going to do is it's going to use this x, this n, and this p, plug it into that binomial equation, and spit back out at me the probability of seeing that number of successes, x, or in this case, 5. Okay? So I hit enter, and the probability that 5 of the 100 are considered millionaires is about 14%, all right, or a probability of 0.14, we round there. Okay. So kind of the format there is you could think about, actually, I'll write it down here right below it. Excel won't be able to do anything with this, but it'll give you a good. So we're going to look for the number of successes, comma, the number of trials, the underlying probability of success, and when we don't want it to be cumulative, we'll use a 0 here. Okay? So Excel's probably going to, yeah, it's not going to like that, but you can kind of see that's the format we'll use. Okay? Well, what if I want the probability x is equal to 10? What's the probability that 10 people are millionaires? Well, I could go back in, and now I have to change the 10. I might have to, what if I update the probability because now I have 2020 data. I don't want to keep going in and updating this equation. So another thing that could be helpful, just like as you're working through the homework, the Connect homework, the Excel homework has a couple binomial questions on it, or once we get to the exam, I'm just going to set this up so that I have my n, my x, my p right here. So n we had as 100, x was 5, 0.067 was the probability that any one person was a millionaire. So I'm going to go back to this equation. Oh yeah, so thank you. So if you comments, if you do that, then it won't treat it as a function, but I did actually want to change this. So instead of typing in the way we did here, I know what should be in each position, right? So instead of using numbers, I'll select my x value here, delete that, highlight my n value there. I'm going to put that p value in that cell. Now it should compute the exact same thing. But the nice way about using cell references is I can very quickly say, well, I don't have to like select the cell and go change everything. What if I want to know the probability 10 people are millionaires, and maybe the probability gets updated to 0.068 in 2020, right? So I can just start playing around, and whatever problem I'm working on, if it's a binomial, I can just start plugging in my probability, my number of successes, right? And it changes that formula automatically for me. Okay? I'll show you how this might be, another way this could be useful. Instead of using the number of successes up here, I've seen sometimes what people will do is So, right, actually, it's easier to do it this way. So, show you the first few. So, fill series, right, and it starts kind of filling it up. So, what's the probability that exactly 0 people are millionaires out of the 100? Well, my number of successes I'm interested in is 0. Number of trials is up here, comma, probably successes right here, and then I'm going to make this non-cumulative. Well, if I copy this down, I want to find the probability of different numbers of successes, but I'm keeping the number of trials the same, so I'm going to freeze that. So remember, Control-T on a Mac, F4 on a regular kind of laptop. Probability of success is going to remain the same, so I'm going to freeze that cell reference. Now when I copy this down, it's going to give me the probability that x is equal to 0, probably x is equal to 1. Notice once I get to probably x is equal to 5, right, it's going to give me the same value. And I can come up with a probability of different numbers of successes very quickly, right? Now, why this might be useful is, I mean, think about it this way. Like, what if I'm, trying to predict the number of, I don't know, lawsuits or something my company is going to face in the year based off of, the past history and the probability I have? Well, I could come up with those probabilities so that I could factor that into my decision-making moving forward, right? I know that the probability that I have no lawsuits, if this was the data, very, very low. So I might want to, be prepared, right? So, this is a nice, quick way to get a lot of different probabilities very quickly. So now I'm going to show you what if I want the probability x is less than or equal to, let's do 5. Right? Well, let's change it from the first example. Let's do less than 6. Okay? So the probability x is less than or equal to 6. Well, what I could do, notice, is actually just add up the probability that x is equal to 0 through 6, right? If I had already had this built over here. However, what if I hadn't done this work, like we start all over, like we're on this sheet from scratch, right? Well, what we could do is say, let's use that binom.dist function. The number of successes that I want to be the last possible number of successes in this range would be 6, right? My number of trials is up here, so I'm just going to select that cell, comma, probably successes right here. It's just now I want to make it cumulative, right? I want to find the probability of 6 successes and any number of successes below it. So the probability of 6 plus the probability of 5 plus the probability, but I don't want to have to like type out, in 6 different cells and then add them, or 7 different cells and add them all up. So I'm just going to put a comma 1 as the argument now, and it will find the probability of 6 or anything below it, right? So it's essentially going to compute all of these probabilities, right? So from here all the way down, and then add them up for me behind the scenes. Sure enough, I get that exact same thing as if I would have done that manually and then added them all up, right? But I only had to do it in one cell, right? Kind of makes life a little bit easier there. Okay. Any questions on that? Yeah.
So when you say true, when
yep.
you put 1 in, it's always like less than, or is that p that x is less than?
Yep. So it's a good question. So when we're making this cumulative, it's taking whatever number of successes you tell it, it's finding that probability, so equal to 6, plus every probability below it. So it's always going to be less than or equal to whatever outcome value you tell it. So I'll use, and I might have to change the slides. I don't think I used 6. I think I used 8 there when I did cumulative, but I'll get this updated, because one thing your question brings up a good point is, what if I want the probability x is, let's say, greater than 6? Well, this is kind of a problem because this formula doesn't have any option to work forward or greater than. But if I think about this as event A, what would the complement be? So if x is greater than 6 is my event A, the complement would actually be what? So remember, there's not 7 options. I stopped at 7 here, but remember, our number of trials was 100. Yeah, sorry. Our number of trials is 100. So, right, what if I'm writing out the complement of x being greater than 6, what would the complement of that be? So here, I could see x is greater than 6, so x could be 7, x could be 8, x could be 9, all the way up to x could be 100. So those are the outcomes in my event A. So A complement would be every other outcome. So if I started at 7 here, A complement would actually be, I could see 6, or 5, or 4, or 3, or 2, or 1, or 0, or less than or equal to 6. Right? Now, so I'm just kind of showing you that so we have it here. Now what I could do is say, look, I know that to find the probability x is greater than 6, I don't have an option with this binomial distribution. But if this is A, I could take 1 minus the complement. Right? But notice here when I'm writing this out, I could put this all in one cell, so I don't have to do it separately. So I could do 6, comma, and then I've got my 100 up here for my number of trials, my probability of success. But I'm going to make this cumulative, right? So now this binom.dist function is going to find the probability that x is 6 or less, which is the complement. I'm then subtracting that complement from 1. That should give me the probability of the event I'm looking for. Okay. So sure enough, I look at this, if I think about these as being, here's the complement, here's the event, these should add up to 1. You can kind of see here they would. What if I wanted to do, this one gets a little bit trickier. Let me come down here and do it here. So what if I wanted the probability x is greater than or equal to 8? Well, once again, I don't have an option with that binom.dist function to move, to kind of go forward or like to go greater than. So I'm going to have to use that complement rule, right? So subtract 1, take 1 and subtract the complement. But here, if A is being greater than or equal to 8, what would A complement be? Being not, so this is where we have to be careful. So if A is that I could see greater than or equal to 8, the complement is that I could see less than 8, right? The equality is on the 8 in this event. So in the complement, I can't see 8. So I don't want to put 8 in here because once I make, so let's say I go 8, number of trials, comma, probability of success, and I make this cumulative. Well, now this binomial distribution function, what is it doing? It's finding the probability of 8 plus the probability of 7 plus the probability of 6 all the way down to 0. But 8, that outcome is actually in the event. It's not in the complement. So instead of 8, what do I actually need to put in here? The next outcome that would be less than 8 is actually, this is discrete, so 7, right? I can't, if I say x is less than 8, the very first outcome that meets that criteria is seeing 7 successes because there's nothing in between 7 and 8. So when it has like a greater than or equal to, it gets a little bit tricky because I'm not using this value in the complement now because the equality is in my event A, so I have to go to the next lowest outcome, right? And then that's how we can compute x is greater than or equal to 8, okay? Any questions on any of this? Want to see another cell again that you didn't get a chance to kind of type in or write down? Or, and I wrote this here just so we could think about the complement. We didn't really need to compute anything here. And then these were just two ways of me showing you can kind of how to think about it. If I really wanted to, right, I could fill that series and find all types of different outcomes. Now notice, if the probability any one person is a millionaire is 6.7%, but the probability I get to 25 out of 100 millionaires, these are essentially probabilities of 0, right? E to the negative 0.9 means move that decimal point 9 places to the left. It's very unlikely out of 100 people we would see 39 of them be millionaires, right? The probability is very, very close to 0, okay? So it doesn't really probably make a lot of sense to keep going with this because we know it's already so close to 0, it's just going to keep getting closer. But for these kind of outcomes between 0 and 10, these probabilities are a little bit more likely for us to see those values. Because what would the mean be here? We'll end on this. You got 100 trials, probability of success is 0.067. On average, the mean should be 6.7, right? 100 times 0.067, 6.7, okay? All right, so we're out of time. We'll kind of end there. We'll probably pick up briefly, talk about the binomial at the beginning of next class, but then we'll move on to the Poisson distribution. After we talk about the Poisson on Friday, that should be everything that we're going to need for the exam coming up. Okay, so no new material next week. I might go over a few more Poisson examples, but mainly review next week. Okay. All right. We will see you guys on Friday.